For a pipe flow, do you remember what is your critical Reynolds number? For a pipe flow, 2000? 2400, 2300, right? For this kind of a flow, for a flow over a flat plate, the critical point will occur at 500,000. You know numbers. So if you have less than this one, your boundary layer will be in the laminar region. When you have more than that, then it will be turbulence or transition. Okay. If you want to split the turbulence further, you will have low turbulence and high turbulence. But okay, remember this. In my class, usually I will use only the low turbulence. I do not want to make you confused with low and high, and then you remember both. Okay, basically most of the calculation that I will use only low turbulence. Okay, so remember that. Now, let's take a look at the comparison between the critical Reynolds number for some cases, right? For flow over a flat plate, the Reynolds number critical will be 500,000. Remember that. It will not be there in your appendix. So if it is there in your exam paper, you need to remember that the critical Reynolds number for flow over a flat plate is 500,000. For flow over cylinder, it will be 300,000 electron volt. And then for a flow inside pipe, 2000 to 2003. And then for the flow between parallel plates, it is 3000. Okay, you know why I put this not equal? Just estimated. Okay, it is just estimated. One researcher has reported their study that they can maintain the flow to be laminar when the Reynolds number reach 100,000. Okay, because the pipe is very smooth, right? And the pump got no vibration. So you keep it smooth. They can maintain the laminar until 100,000. Which means this one is just a rule of thumb. For certain condition, maybe at 1,000 you already get turbulence. Okay, but this one is just good for engineering estimation. Okay, now, Reynolds number will determine whether your flow has been moving from laminar region to turbulent region. We want to look further. What is the effect of Reynolds number to the boundary layer thickness? It turns out when your Reynolds number is increased, the thickness of the boundary layer becomes smaller. But you said that as the Reynolds number increase, the boundary layer become bigger. Okay, this is two different stories. Okay, let me explain to you. Let's say this one velocity is 1 meter per second. This one velocity is 10 meter per second. When you have 1 meter per second, the boundary layer will grow from here to there to there. Right? This is the thickness, is delta 1. In here, when your velocity is higher, Reynolds is when phi higher, Reynolds is also higher. Right? So in this case, the boundary layer will be thinner. Okay, so at the same location, if the velocity is higher, your boundary layer is smaller at the same location. Of course, as you go further, the x is increased, right? When the x increase, Reynolds also increase. Of course, your thickness will increase. But when we are talking about the same location, for the higher Reynolds number or higher velocity, your boundary layer is thinner. Boundary layer is thinner. When the boundary layer is thinner, the friction is smaller, right? Because the viscous effect is smaller. Okay? So when you design your aircraft, you need to make it in this region. You have to make it very thin. Okay? Now, one example, I think I need to explain you this. You are playing a kayak in UTP Lake. I do not know how many of you love to do that. If you look at the canoe or kayak, you can treat this kayak surface, bottom surface, as a flat plate. When it is as a flat plate, you treat it. Of course, it is not ideal because kayak, you cannot have that. Unless you have swam boat. You know the swam boat? That boat that has a big fan over there. Usually, if you are crocodile hunter, right? You have this, right? For that swam boat, this one is really a flat plate. But okay lah, we treat that as a flat plate. Make our life easier. So you have that, and then you are moving at 7.2 km per hour. Okay, you refer to the figure. The bottom of the canoe can be treated as 5 meter long plate, and it is flat. The temperature is 20 degrees C. So now you need to find out whether the boundary layer on the canoe bottom is laminar or turbulent. How do you do that? You need to calculate the Reynolds number. Okay, so if you want to calculate the Reynolds number, what do you need is rho v x mu. Rho you get it from the water properties at 20 degrees C. Mu similarly. How about the phi? Okay, you get it from that because when the canoe is moving, we know that the water is stationary, right? So we treat it such as the water is coming to the canoe, like what we have. It's actually the canoe which is moving, but from the point of view of the canoe, it is the water that is coming in. Relativity. Theory of relativity. Okay? So you get that 7.2 as your velocity. Then you can calculate your the Reynolds number. In this case, the Reynolds number is 9.96 times 10 to the power of 6, which means 9 million. Right? 9 million is very huge as compared to 500,000. Okay? So you can treat the flow as a turbulent. But that one is at the end of the canoe. How about the other part of the canoe? How about the other part of the canoe? You do not know yet, right? Because it will change from laminar into turbulent. So, in this case, I will take just 10% of the length of the canoe. The length is 5 meters, so I take 0.5 meters. I found it 9.96 times 10 to the power of 5, which is still above the threshold. So I can safely say that the canoe is in turbulent region. Okay. This one is okay, but if somehow my velocity is only 0.5 meter per second, right? Only 0.5 meter per second, you will be sure that at 10% of the canoe, it will be still in the laminar zone. What is the effect of this? In the next class, I will show you that the boundary layer can have 3 different cases. one is fully laminar, the other one is fully turbulent, and the other one is mixing between laminar and turbulent. So this kind of thing is important when you want to decide whether you have a mixing boundary layer or you have a fully laminar or fully turbulent boundary layer. Okay, so that's all for today.